All right, our new unit is circuits, and we're going to begin with just a little review on all of the parts of a circuit. And the first part we're going to think about is voltage. So if you remember from the last unit, a change in voltage is equal to the change in electric potential energy divided by the charge of whatever particle is doing it, or that's equal to the work divided by the charge of a particle. And remember that we've got a positive plate here, negative plate here. Then we have an electric field that flows this way. That's the direction that a charge wants to go. Our high voltage is on the positive side. Our low voltage is on the negative side. And remember, it's kind of like potential energy, where you can define zero wherever you want it to be, but it's the difference in voltage that makes the difference. I can define the ground as zero. I can define the top of a building as zero. It's just going to depend on the problem that we're doing, and it's arbitrary because it's that change that matters. So when we look at a battery, what creates the voltage? It's the fact that you're going to have a metal in an acid, and when that metal dissolves, it's going to create a positively charged ion, which will then strip electrons off of a donor. And as those electrons get pulled off to ripped over to the other side, that's going to create a charge, a current. So as long as you can replace them, now, if you connect those two sides, now you can have a current that flows. You can have electrons moving. Over here, when we look at this, the way batteries work is basically you just have a place of high potential and a place of low potential. So this is like a pre-made one where you got a source that can donate a lot of electrons and a place that is really short on electrons. And as soon as you give it a pathway to flow, then those charges are going to be able to start moving through and balance out. Because remember, things want to flow from high to low potential. If we've got a high potential over here, low potential here, understandably, and this is confusing, when they first made current, there's no way to tell the difference unless you're looking at a microscopic level on whether positives are flowing one way or negatives are flowing the opposite. So the way we show is that charges flow from high to low potential in actual, in terms of electric current. But when you know, just remember electrons are flowing in the opposite direction of what current is flowing. It's confusing, but we'll make sure we go over it so that it sticks in your brain. So we have a lot of excess electrons over here that are on the low side, and they want to always get to a higher potential because remember that negative charges flow against the electric field. Electric field goes from high to low potential. So those electrons are going to go this way, and that's what causes a light bulb to light up when it's connected. Now we're going to do a little review on current. Remember, current, all it is just the amount of charges flowing over an amount of time. And the units of current are charge is coulombs, time is seconds, so it's coulombs per second, and the other way you can write that is A, as in the ampere. Don't call it amperage, it's the amount of current in something. And then the other thing, which we had just talked about, is that conventional current flows from positive to negative. So this is conventional current. The way your electrons flow is the opposite way. That's the way that electrons go. So remember, conventional current, opposite of the way that electrons flow. The other way you can write this, and it's the symbol that represents current, is I. And this hopefully is just a little reminder of how circuit diagrams work. All right, now for our resistance review. Resistance is equal to voltage over current. And remember, units of voltage, volts, current, amps. If you take volts over amps, you get a capital omega, which is an ohm. And it's the unit that measures how resistive to flow a substance is, of a flow of electrons, which, as we look right here, resistors control the flow of electrons. So for a given voltage, the higher your resistance, the lower the current. So the more you resist the flow of electrons, that means you have a higher resistance, that means you get a lower current. Now, Ohm's law up here is only true for ohmic resistors. An ohmic resistor is basically one that follows Ohm's law. So if you graph voltage versus current for Ohm's law, you get a constant slope, which means that your resistance is going to stay the same. That's true for most metals. But any object that's not a metal, or some of the rare metals that aren't, or at extreme currents, things start to break down. What you'll see is to get a linear increase in current, you need an exponential increase in voltage. All right, so resistivity. Very closely related to resistance. It's just how much a specific material or amount of material is going to resist the flow of electrons. So there's a couple different factors, but the main thing we're going to look at is that conductors have low resistivity, while resistors have high resistivity. And there are technically there are 4 different things that are going to affect it. But I want you guys right now to pause the video and attempt to figure out, as I increase these factors, what's going to happen to my resistivity. So as I increase length, what happens to it? As I increase the area of whatever it's flowing through, what happens to resistivity? As I increase the temperature, what happens? Take a second, pause the video, find out on your own. Okay, we'll see if you got it right. So as we increase the length, it's got more material it has to flow through. It's obviously going to increase because it's going to have more stuff it has to travel through, meaning there's going to be more resistance building up on the way. As I increase the area, think about it as like kids walking down a hallway. If I increase the side of the hallway, if I've got a hallway full of people, they're going to be bumping into each other. But if I make it really big, they're less likely to run into each other. That's going to decrease the resistance. You can almost think about it like heat flow too. When you make that area bigger, heat can flow faster. There's less resistance, more current, bigger area, then there's going to be more heat that can flow or more electricity that can flow depending on your context. And then temperature, think about it as that same hallway, but now we give the kids like a whole bunch of caffeine and we get them all jazzed up and we try and make them run down the hallway. They're going to be bumping into each other a lot more often. That's the same thing with temperature. We're giving the particles way more energy. Therefore, they're going to be bumping into each other through random motions. So we're going to increase our resistivity through that. The material also affects it too. This is a list of the least resistive materials, starting with silver, copper, gold, and then so on. It just keeps going up from there. But these are your least resistant ones, which is why you see copper used mostly in our electronics because it's a lot cheaper than silver and it's not much worse at conducting electricity. But when you need small amounts of gold and silver, they are used in specific electronics, especially because gold is very resistant to any type of chemical change. As we come up here, we're going to look at the formula for resistivity, which is just going to be, we're looking at our factors over here, rho L over A, where I know this is a little confusing. You think of rho as density, but in this case, it's the resistivity value. It's the amount of ohms every meter. So it's measured in units of ohm meters. Temperature does get related in because we see it over here. Resistivity comes down to this factor. We have area, which is inversely proportional. We have length, which is directly proportional. But what we need to see is that resistivity is affected by temperature. So your resistivity is going to be equal to whatever the temperature they originally measure at to find your temperature coefficient. That's going to be your T naught. And the new temperature at is going to be how your resistivity gets affected. For most metals, this is a very low value, which is why we can assume they're ohmic. They make pretty much straight lines because their resistivity doesn't change based on the temperature that they're at. However, it does start to add up over really big temperature differences, and that'll do it for resistivity review.